absolutely right. Sorry. Right. Oh, wait. Oh, am I good now? Okay. Sorry. Oh, yes, you can hear me. All right. Sorry. So sorry. That was totally me. That was not you. And thank you for, okay, I'll start again. Thank you. God. Yes, that was totally me. Okay. And it's so funny. Right. No, nothing on my end. Okay, wait. And now more people are coming in here. All right, I'm gonna pause for a second and start all over again. But thank you. Sorry. You missed nothing, clearly. Well, even if you missed the whole class, you probably missed nothing. But okay, hold on. Sorry. Hang on. Oh gosh, I'm being called. Hold on one second. Yes. Well, I'm in the middle of class right now. I love you, but I'm in the middle of teaching. What's up? Well, that's actually a great idea. I think we'll go. Well, we'll look at. I think both of us will be very excited. All right, well, let's look into that. Okay. Great idea. I'm gonna go teach now. That's a great idea. Good talk, everybody. Mom and I agree. Yeah, great idea. And thanks. Hey, Felix, even though I was teaching, thanks for telling both of us at the same time too. That was a really nice idea to tell us both. We're gonna look into it. Okay, sorry. Okay, I'm back. Hang on. Give me one more second. I'm sorry. Hold on. Okay. Okay, the board is coming up. Okay, so I think I'm going to start all over again. Okay, there's the board from yet. Wait. Okay, as I mentioned, I really do hope to meet you all in person, whether it's in 204 or in life. But it's going to be really disappointing when if we all do meet, and hopefully sort of post-COVID or whatever, you're going to find out that I am just this spazzy, whether or not it's COVID. I love to blame everything on COVID, but actually my personality has nothing to do with COVID at all. All right, I'm going to start again, or my incompetence. Okay, I'm going to start again here. I think, yes, good morning, Luna. Good morning, Zitlali. Good morning, Noelia. Good morning, Molly. Good morning, Darina. Good morning, Sonia. Good morning, Nikaya. Good morning, Daniel. Good morning, Amarani. Hello, Jennifer. Good morning, Camilla. Thank you for the tip, Daniel. Thank you for the tip, Amarani. Thank you for the tip and good morning, Jean-Pierre. Thank you for the tip and good morning, Molly. Thank you for the tip and good morning, Sonia. Thank you for calling me good. That's the nicest thing I've heard all week, Molly. Okay, thank you, Jean-Pierre. Thank you. Oh, good morning, Michelle. Thank you, Camilla. Thank you, Jennifer. Okay, thanks, direct message person. Thanks for asking, although I'm totally lying, but I don't know how transparent that is. Good morning, Melissa. Good morning, Alyssa. Good morning, Aja. My kid said, well, you could hear that part about karate? Oh, yeah. Okay, well, good, thank you. I'm okay, sort of, thanks. Not really lying, but probably better than you guys. Maybe, well, I don't know. Anyway, we'll find out. Okay. Oh, wait, someone's coming in. Sorry. Okay, what Michelle said at the end of the chat is funny. And yeah, I mean, I guess that's true. Yeah, that's true. I wouldn't. I guess you would recognize me, although, wait, there's people in the waiting room. Sorry. And I know we should get rolling. I should not be stalling, but wait, I can't get these people. Hold on. Okay. Yeah, well, I do hope I meet you one way or the other, and you probably would recognize me, although I probably might shave if I ever go back to reality. I don't know. Also, my office is very hidden on purpose. So, but anyway, all right. Good morning, Catherine. Good to see you. Okay. And nobody's missed anything. We're just getting warmed up here, even though I know we have limited time. Okay, and I'll say that. Well, oh, and good morning, David. So I think that's okay. Yes. Good morning. we're going to get back to exactly what we were doing before, which is, in case you don't, in effect, what we're doing right now is we are working through the final. Now, again, let me also say a couple things. I'm intentionally not, and we still will meet this coming Monday, as you know, and everything we say about Monday really will be like directly our last words about the final and stuff. But that's what we're doing now too. Just also to alert you again, a couple of things. I say that what we're doing right now is about the final, and that is true. Like everything I'm trying to show you right now is literally ultimately so that you can answer the questions on the final. But you have, the rough draft of the final in your box now at this point, hopefully, and you'll notice that there are answers there. So I'm trying to teach this now like teaching, right? I'm not doing it right in the final with you because that's already done in your final. So this is hopefully an explanation that'll make more sense, help you make more sense when you look at the solutions that are in the final. And they might even be intimidating to you right now. I don't know. So, but we're intentionally doing this like on different pages. Okay. So then when you look in the final and you're looking at my answers, but my answers will make more sense due to what we're doing right here. But again, that's like, so I'm just trying to get at it from whatever angles. It is deliberate that I'm not just like walking you through the final like right now. Although again, by the time hopefully you've looked at it by Monday or something, and then Monday maybe we'll have it right in front of us. Maybe. Now, as far as your midterms, which I still don't have, and it's getting ridiculous. Well, it got ridiculous a long time ago that I didn't have them. And look, and there's no good excuse. Even if I had excuses, they're excuses. They're not good reasons. I'm sure it's also becoming one of those ridiculous things at this point that the longer I take, the longer it's taking me because it's becoming some sort of ugly block. And I apologize. But there's one thing I want to offer you all, and I will get them back. I keep saying I will. I know by the time you get them, it's like ridiculous, but you did work on them. You deserve to get them back and to know what's going on before you take the final here. And I don't want to spend too much more time like apologizing or talking about that. But I did think about this while I was scrambling this morning, and I realized there is one important concession I can make to you that I've made in the past that I almost forgot. And I want to tell you that right now, whether I put it in the Google Classroom or not. What I'm going to tell you right now, you did work on these midterms. So no matter what, whether your work should not be thrown away or forgotten or ignored by the universe, and it won't be. And I won't discount it. But I will tell you this right now for anybody who's listening. One, the most fair, the way I can make this a little bit more fair or a little bit more right for all of you, and I mean this, what I'm about to say, I don't know how many times I will say it, but what I will do at the end when I'm scrambling to grade all these things and when I get your final exams in, I will tell you right now that whichever of the two exams, of the midterm exam that you have not gotten back yet, and the final exam, of those two exams, whichever you do better on will count for you a lot more than the other one. And that may differ from person to person. Let me say that again. Like, I'm not going to throw away one of them, I don't think, because I think that will be unfair for other reasons. So I'm not going to throw either one away. But whichever one you do better on, whether it turns out to be the midterm or it turns out to be the final, I will count a lot more heavily in the average. Like I'll do a 3-to-1 thing or at least a 2-to-1 thing. In other words, if you do better on the final, I'll count that like 3 times and your midterm like 1 time. Or if it turned out you did better on the midterm, I'll count the midterm like 3 times and the final like 1 time, something like that. I have to think through the numbers exactly, but I will do that. I will heavily weight whichever one you did better on. And that will obviously differ from person to person. So that's the one way I can promise you that if you did hard work on the midterm, even though you haven't gotten it back yet, it's going to help you a lot. It'll give you a cushion, even if you don't know it right now, if you end up wavering on the final, or vice versa. If it ended up that you did really bad on the midterm and you're only finding that out like 5 minutes before the final, then the one concession I can make is your final will count a lot more. Okay. So for all of you, whichever you did better on, whichever one you did better on, I'm going to count a lot more than the other. That's just all I can say about that at this point. That's in recognition of the weirdness of not having gotten them back yet. Okay. And you still will get them, but that's what I'm saying. So now, if that makes any sense, and we are recording, I want to go back to exactly what we were doing. But please, in the private chat or whatever, let me know if that troubles you, or if that didn't make sense, or you think you just heard something significant, but you think you might have missed it, because I did just say something significant about your grades. So if you're unclear or unhappy about that or something, like private chat me and I'll catch it, or whatever. Or can I just get a thumbs up that you all heard that? You are hearing me right now, right? Like, or wait, have I lost you? Wait, can you hear me? You can hear me, right? Yes. Okay. Great. Okay. Thank you. Okay. All right. Cool. So now I'm going to go back to exactly what we were doing before. Okay, great. Thank you. Awesome. I totally appreciate it. And that's thousands of points. And by the way, I think you know what? I'll tell you this too. Yes, I wouldn't recognize, right. Unless one of you actually looks like a black square. I mean, literally a black square. Then you're right. I wouldn't recognize you in the halls of John Jay, but I'll bet you with almost all of you, if you said a couple of words to me, I would pretty quickly know who you were from your personality. I like to think that. Well, maybe it would take more than a couple of words. Anyway, all right. Okay, thank you. I appreciate it. Whew. Okay, I would certainly recognize your emoticons, right? Okay, so the very last thing we said yesterday was that if you, and so I'm right here, I'm in the same packet of notes as yesterday, not like, okay, but I will repost them when we're done. If you have an object sitting on a table, then from now, if it's sitting on a table, it's got two equal and opposite forces acting on it, right? Oppositely directed as these arrows indicate, and they would be equal. They would be equal, as my little blue lines are sort of meant to remind us. They would be equal because F net equals MA. Because if something's sitting on a table, its acceleration must be 0. So that must mean the net force acting on it must be 0. And that could mean that there's no forces acting on it, but that's clearly not the case here. There are forces acting on it. So it must mean that one force plus the other, taking into account direction, must equal 0. So in a case like this, in other words, what's the point of this diagram? So the whole purpose of a diagram is it tells you all the things to plug into the left side of F net equals MA, so as to find what's on the right side of F net equals MA, so as to find the acceleration. Or sometimes we go backwards and we know the acceleration, we're finding the forces. So in a case like this, what we would say so the left side says add up all the forces, all of them, add them up, add them. That's what sum means, right? But recognize that forces are vectors, they have direction. So you add up all the forces along each axis, taking into account direction. So in other words, what's really going on here is I add up all the forces on the y-axis, and I'm going to say that the sum of all those forces on the y-axis will produce the acceleration along the y-axis. Hence, I put those little y subscripts there. Okay. I would also say, it means if I added up all the forces on the x-axis, that would produce the acceleration along the x-axis. Now, it happens in this picture, in this particular case, there is nothing happening along the x-axis, okay? So it's like 0 equals 0, okay? But on the y-axis, what we have is what we're now, from now on, calling the normal force pointing in one way, plus the other force, the mg force, but that's pointing in the other direction. So strictly speaking, what I'm saying is this, right? And this is the way F net equals MA always works. F net equals MA is really, it looks like one equation, but it's a vector equation. So what it really means is a separate, an independent but simultaneous equation applying to each axis, like independently but simultaneously. And on each axis, we're adding up everything, but we're accounting for negative signs. I mean, we're accounting for the difference between left and right or up and down, blah, blah. So what we're really saying here is n up minus mg must equal ma. And in this case, we happen to know, we just declare we're talking about something that's sitting there on the table. So we know that A equals 0. Hence, and I know I'm making this totally illegible, but hence we know n minus mg must equal m times 0. Therefore, the normal force up equals the gravity force down. And that's all we could say about this case. Why am I making a big deal about this case? Like I'm trying to, again, I'm trying to progress toward the case of your lab. But there's two things I'm just trying to say here. One, I'm saying these forces are equal and opposite, but not because of Newton's third law, because of Newton's second law. That's because we know the acceleration is zero, therefore we infer or we see that these two forces must be equal and opposite. That's number one. Number two, kind of, or the bigger point almost, is that I'm saying from now on, that up arrow is called the normal force. What I was trying to say, and this is like, you're going to see this diagram so much in your life or in textbooks or whatever, especially if you ever do physics again. It's that N stands for normal, and normal is a terrible word. It really is a terrible word. It makes us think, maybe unconsciously, when we hear the term normal force, a lot of people think like, oh, the force that's like normally there, that's like always or typically there, or the force that like counteracts gravity or something. Well, often that's what the normal force is doing. Often it does counteract gravity, but there's no law that says it does. And there's no law that says that the normal force always has to be there. For example, if you just drop something like our first free body diagram, then the only force acting on a falling object is just gravity. When something's in free fall, there is no normal force at all. Or furthermore, if something is being suspended by a string, let's say, like if I'm holding something still, like a fish on the end of a fishing line, then in that case, what I would have is the weight of the fish down, but what I'd have up is the tension in the string. There's no rule that says a normal force always has to be there, nor is there a rule that says the normal force always normally has to counteract gravity. And we're going to see in a moment on the inclined plane, it does not fully counteract gravity. What normal means, and yes, it comes up all the time, so we have to know it. What the normal force is, we were saying yesterday, Monday, is the pushing force of one surface against another. It's called normal because it's the force that goes perpendicular to the plane of contact between any two surfaces. Like it arises whenever one surface pushes against another surface, i.e. perpendicular to the plane of contact. Normal means perpendicular. Okay, so yes, it's frequently there in our pictures, in our free body diagrams, but it's there if a surface is pushing another surface. Now, okay, so let me look in the chat. Let me just look in the chat. Okay, okay. But please do stop me, like in the chat, and really, I mean, if there's, but anyway, because I'm going to go on now. Now let's like apply this to the lab. Let's go one step more complicated, or actually two steps more complicated. If we get to the lab idea, lab 5 now, there's two more features that increase the complexity of this. One, in the lab, your table is tilted, right? Everything's at an angle, and that, maybe I should say there's three factors. One, your table is tilted. Two, because it's tilted, things are now sliding on it, like they actually are accelerating. At first, they're accelerating because you push the thing up, and then you let it go to the top, and it accelerates down. So two factors are: one, we tilt the table; two, there is actually motion and acceleration going on; and three, because there's motion and acceleration going on now, the object is sliding along that surface, that desk, that tabletop, whatever you call it. And so then friction comes into play. Now, and so let's look at that now. One thing I'm arguing, though, is friction is just a fancy word for the pushing force parallel to the plane of contact. One thing I'm trying to argue, or was trying to argue Monday, is that friction is just the other component of normal force. Friction and normal go together. They are the two perpendicular components of a phenomenon that occurs whenever one surface pushes another surface. Okay, so we're going to deal with all three of these factors now as we look at the lab and tilt this whole situation onto an angle. number one, so the whole situation that we're looking at now, the lab situation, is strictly called, or classically called, the inclined plane. I mean, plane meaning surface, and inclined meaning elevated to an angle or tilted, right? Galileo worked a lot with these inclined planes and inferred a lot about gravity, acceleration, forces, and then Newton continued the work. But the inclined plane is sort of a classic physics setup. And one reason for the inclined plane is that it allows us to look at gravity. It allows us to look at the effect of downward acceleration, but on a tilt, on purpose, by tilting things a little bit, but not a lot. We're in effect diluting gravity. We're slowing the whole situation. We're slowing the whole free fall situation down, so we actually have time to look at it and get good data. But that's what it is. It's like a way of slowing down gravity. All right, so let's go to the next page. Hang on one second. Okay. All right. So the situation Okay, so first I'm just going to draw. Oh, someone's here. Sorry. All right, I'm going to sketch the situation, and I want to make that distinction clear. I'm going to sketch the situation. It's not the free body diagram yet. It's just a sketch of the facts as you would maybe put on an exam or whatever. And the large reason for sketching this before even doing a free body diagram was, first of all, so you can see all of the factors going on, and so we can label, so we can assign variable names that we're going to use in the equations. But also, the real reason I'm going to sketch this first is so that you can see in my head which way things are oriented, and then we're going to use that orientation consistently through our free body diagrams. In other words, here's, so this is a sketch. This is not a free body diagram. A sketch. I'm assuming, so I'm saying here's the, I probably should. Okay, this is a sketch. It's very sketchy. The main, I guess we could say this. Okay, the main purpose of this sketch, again, is to introduce all the variables that will be used in our equations. It sort of defines the variables according to this picture, but so we have a mass m on some sort of plane that's inclined at an angle theta, right? And notice, and like, physics is getting more physicsy now. So I'm not using numbers, I'm using letters, because I'm saying this would be true for all time, whether your theta is 30 degrees or 20 degrees, like all the facts that I'm going to say about it are going to be the same, no matter what the number is. I'm definitively saying here, so I'm including the m, I'm making it clear, or trying to make it clear that the ramp is rough. That's like what the jagged lines are. I'm saying, and maybe in your lab it went the other way, like I don't know, but I'm just saying here I'm picturing a ramp that's going the way that it's going, from bottom right to upper left. That's an arbitrary decision on my part, but I'm going to stick with that when I do like any free body diagram I do now will be assuming that orientation. Let me write it. Okay. Again, the orientation is arbitrary, but it matters because I'm going to have to stay consistent with it. Okay. And notice I'm telling us, okay, there's a G, like we are on Earth, there's gravity coming down. And I'm specifying V0 does not equal 0. Like, just like in your lab, someone pushed or tapped or like knocked this mass so that it started going up. Like I'm taking a photograph or a mental snapshot of some moment when the mass was on its way up. It's on its way up because someone thrusted it up, but they just gave it an initial velocity of something that was not zero. And then they let it go. Like, so there's no hand pushing this thing anymore at the snapshot or the moment in time and space that we're now going to investigate, right? The thing is moving because it initially was moving. And Galileo's principle applies and Newton's first law applies, right? Okay, so now so that's the sketch. Now I'm going to draw the free body diagram of some of this arbitrary moment in space and time, like during its ascent of the situation. So I'll even say this almost. Okay, so we're talking about the up trip here, some moment in the up trip. I'm now going to draw the free body diagram. And again, and this is sort of, you might notice if you're looking at the exam next to you while I'm doing this, you'll notice this is about to be sort of what the exam asks for. Okay, so first we draw a free body diagram of the object at that arbitrary moment during its up trip. Okay, so what am I supposed to do? I'm following the rules of free body diagram. First of all, I draw a point that represents the mass itself, the center of the mass. The first thing I do always, actually, let me mess up more rooms there. Okay. First thing I do is draw a downward force called mg, which is the weight of the object. That is in every single diagram always, because every object has weight. Every object is being pulled toward Earth, like always. Then what do? Then once I've drawn gravity, always first, then I draw an arrow for every other force that's acting. How do I know what other forces are acting? And this goes back to last week. I look at any and everything touching this object. Super important. I don't make up forces. And I'm not drawing velocities. I'm not drawing things just because I think there's motion. I don't overthink. I just draw an arrow representing anything and everything that's touching this object. Okay. So the first thing that's touching this object is the desk, the plane, the surface underneath it, just like we had in the last diagram. And like there's a surface underneath the object and it's pushing against the object. It's like supporting it somewhat, not as well as a desk would support, but we've got some plane underneath the object supporting it or pushing against it, if you like. And the name for that against pushing thing, we said, is the normal force. So I'm going to draw the normal force here, just like I did a minute ago. But remember, normal means perpendicular. It means the force of push perpendicular to the plane of contact between the two objects, and between our object and the surface pushing against it. And look at my picture, like the plane of contact is like this, according to my picture. That's the plane of contact, the plane against which the object is making contact. So the normal force must, by definition, be perpendicular to that. Just like if the plane were horizontal, the normal force pushed vertically up, right? So same idea here, the plane is now tilted. So the normal force is tilted. And maybe that's obvious, but maybe it's not, I don't know, but it's true. So if I follow the orientation of my sketch, I draw a normal arrow up on a tilt like that. Okay. Now, no, and I'm going to, in fact, I'm even going to, one second. I'm not changing anything, but I'm just making it more clear. Like gravity was this weight pulled down, and now the normal force on a tilt. What I want to make clear is now that this thing is on a tilt, I want you to realize there's no reason to just assume that the normal force just automatically balances gravity. In fact, if it did, if the normal force fully balanced the weight of this object, then I don't think the object would slide down it or up at all. Like, it wouldn't slide. So I want to get out of so the normal force is just the push perpendicular to the plane of contact. I have no reason to assume that the normal force automatically is balancing anything. And in fact, it isn't. Therefore, I did not make the arrow the same size as the other arrow. Okay, now again, these arrows are even these arrows are like approximate. We don't know exactly what the sizes are until we work out all the math. So it is approximate, but I want to, like, right away make it clear that that normal is not necessarily equal in size to that mg arrow, and I'm even guessing that it's going to be shorter in size, or like weaker in magnitude than the normal force. Than the gravity force. I'm guessing that it's weaker because the object does slide. Sorry. Oh, great question. Hold on. Okay. Right. Okay. Great question in the private chat. Okay. I'm not going to say the person's name because it is in the private chat, but I'm totally going to read the question out loud because it is a big point. So the question says, does it matter which direction that I draw the normal force arrow, like as in slanted to the right or the left? Great question. It totally does matter. And the way I chose to draw it is I'm looking at this picture and I'm looking at this picture and I'm saying my arrow has to be drawn in a direction that's consistent with this picture, which you'll notice doesn't mean identical, it means consistent. In other words, I'm saying if according to my sketch, the whole plane, and I keep doing this weirdly with my hands because I'm like in a mirror image of the, hold on one second. I think, hold on one second. Okay, that's so weird, but I think this might help. No, I still can't. Well, all right. What I'm trying to say, this is a great question in the private chat. Notice, and please, when I'm done answering this, please tell me in the private chat whether I answered or not, because this is super important. It's a great question. Notice that the plane is going like this in my picture. That means, according to my picture, the normal force, by definition, has to be perpendicular to the surface. That is actually what normal means. It means perpendicular. And it also doesn't mean anything else besides perpendicular. People always think that it does. It's a really easy trap to fall into. But the normal literally and fully means perpendicular. So if my plane, if my plane is going like that, then my normal force has to go make a right angle with it. So my normal force in my picture is very deliberately going from down left to up right because my plane was doing the other thing. If you were on the final exam, say, and if I just add, you could make your original sketch go the other way, especially because maybe it did in the lab. I don't know. Maybe in the lab, your actual plane was tilted the other way, and that's totally fine. That's just reality. But then you have to make your normal force go the other way. The normal force has to be perpendicular to the plane. And then please but tell me in the private chat if that answered or not. But that's a really important question. But let me put it one last way. The normal force is frequently playing a very important role in these problems and diagrams, but the only thing we know about it is what I just said, that it is perpendicular to the surface. Okay, and well, all right, so I'm going to keep going, but let me know if that made sense or not, because now I'm going to say, and maybe this will also help, I'm going to say, okay, the rule is, the arrows that we put into these diagrams, each arrow is only supposed to represent a force. The point of the arrows is to diagram forces. And the way we know about forces is, first of all, we always put the force of gravity in because it's always there. And it has this weird property of existing without touching. But since it's always there and it has that weird property, so we otherwise might forget it, we put it in first. After gravity, everything we put in is a touch. Okay? Everything, and the only things we put in are touches. But there is this one odd factor about touching. And we said this last week in preparation for this. So let me write this down here. Okay, there's other ways I could put this, but so I'm saying again, how do you draw these diagrams? And if you look at the final exam, you'll see we're very obsessed with these diagrams. Like they're super important. And in a way, they're much easier than they sound, but in a way, until you get used to them, they might be harder than they sound. All that you're supposed to put in these diagrams are forces. You always put the force of gravity, and then you just put one force arrow for every touch. However, when surfaces push against each other, they touch in two ways. And everything else, like when it touches, everything else you can ever imagine, like a string pulling or a hand pulling, everything else pulls or in one way, and then that's the force. But when surfaces push against each other, they touch in two ways. One, they touch, or when surfaces touch each other, they push in two ways, I should say. The surfaces push in two ways, I should say. I'm sorry. Hold on. Well, I don't know which is the better way to put it, but what I'm trying to say is right from the get-go here, we talk about gravity. Oh, okay, thank you. Great, I appreciate it. And I doubly appreciate that you would say that. Cool. Okay. Private chat person. Forces are pushes or pulls. There's one pull or push that ever happens without touching at all. That's gravity. That's like one exception. So we always put it in first. Then there's one other exception to the, like what I used to say in classes, and you can write this down if this makes sense to you. Like what I used to say all the time is there's the one touch, one force rule. For every touch you see, put in one force. End of story. But there's two exceptions to that, and only two. One is gravity, because somehow it pulls without a touch. So we always put it first and we don't forget it. And the other exception to the one touch, one force rule is surfaces pushing against each other. When surfaces push against each other, or when surfaces touch each other, they actually push in two ways at the same time. One, they push against, and we call that the normal force. But then, because all surfaces are at least microscopically somewhat rough, whenever they push like this, they also push like this along the other axis. That is, whenever there's a normal force acting in real life with actual real surfaces, and especially when there's motion involved at all, whenever there's a normal force, there is also a friction force. And that goes parallel to the plane of contact and against the direction of motion. So what I'm going to say right now, okay, is that in this diagram, there is, because this thing is sliding up, there is also in this diagram an arrow called the friction arrow, and it's pointing down and to the right, like down at an angle. We call this arrow lowercase f for friction. Okay, I'm saying in real life, whenever you have a friction force, you better have a normal force as well. They are part of the same phenomenon. And whenever you have a normal force, you better check, could there also be friction? Maybe friction isn't relevant if the thing is just like sitting still, then maybe it's not relevant, or maybe it won't affect your calculations. So maybe sometimes we can ignore it. But friction comes with normal comes with friction. They are just the two perpendicular components of the overall phenomenon of surfaces pushing against each other. Okay, so I put the friction, and how did I know how to put the friction? And I'm sorry, I'm like yelling and screaming, but hopefully you can write this down. How did I know? So how did I know that there was friction at all? Because two things were pushing against each other. How do I know where to write the friction or how to point it? Friction has to be parallel to the plane of contact. That's what we said last week. And it has to be against the tendency toward motion, as I think you would guess. In other words, right here, the object is on its way sliding up. So friction is going against its motion, pointing down. to clarify, like in a minute, or if we ever, when we get to the other diagram of the situation of the thing sliding down, then friction's going to flip and point up, and that'll make a big difference. But this is my diagram so far of a arbitrary moment during the object's ascent up the plane. I'm very deliberately, like not coincidentally, I'm saying these two forces, I mean, you don't have to put this in your diagram, but I'm just trying to tell you these two forces, normal and friction, are at right angles to each other and always are, by definition. So what, okay. Now, so far I have these three arrows in my diagram. And please also notice, like normal and gravity are not parallel, right? Normal and friction are perpendicular. Gravity is off on its own thing, just pointing straight down. And this is all because the whole plane was tilted. Now, remember, I'm trying to draw a pure free body diagram. I'll tell you what I mean by pure in a moment. Well, but pure means the original free body diagram just as is, with no math or nothing being done to it, just the original diagram. Now, remember, I'm supposed to draw an arrow for every force acting. I'm telling you again, that means an arrow for gravity and an arrow for every touch that you observe, just recognizing that when surfaces push, they actually touch in two ways, not one. So again, there's like two exceptions to the touch rule. One is gravity that seems to act without a touch, and two is surfaces pushing, which seem to exert two touches whenever they press against each other. Anything else, so we've done those. So I always sort of think about those first because they're sort of the trickiest. Now, anything else that I want to put in this diagram better be a force, and any other force that I put in this diagram better be because I see something touching the object. And I'm going to tell you right now, I mean, because of limited time, there's nothing else touching this object. There is nothing else touching this object. Let me be very clear about that. I know the object on its way up. So I know for that to have happened, you probably had to shove it initially, like with your hand or something, and you did. And we called that an initial velocity in our sketch on the previous page. But we're now looking at an arbitrary moment somewhere during the ascent. You're not touching it anymore with your hands. You might have had to at one point to get it going, but it's still moving now without you touching it. Maybe it's slowing down, but it's still moving. And we're still interested in it. And you're not touching it with your hand anymore. So your hand does not go in this diagram. The initial velocity that I designated in the previous sketch also is an important fact, but does not go in this diagram. This is only a diagram of forces. So there's no initial velocity, there's no hand. And also you might say very reasonably, or someone, I mean, if you're with me so far, you might say, okay, but like, how's the thing? But the thing's moving up, right? Like, doesn't there have to be like an up arrow indicating that it's moving up? No, like I know the thing is moving up. But we're not looking at motions. We're looking at forces. And we're looking at forces because they ultimately are going to tell us about its acceleration. And I'm going to tell you right now, with it, trying not to give anything away, this object might be moving up, but I don't think it's accelerating up. I think, if anything, it's accelerating down. What do I mean? I mean, even though it's moving up, I bet it's probably slowing down, right? Like, I don't think it's accelerating in the same direction that it's moving. I think it's accelerating negatively, and that's why it's eventually going to stop, right? Now, that's all just like advanced knowledge or intuitive knowledge, but that's all to argue. Like, there's a big tendency people will think, well, there's got to be some arrow pointing up because otherwise, like, why is the thing going up? No. There is nothing pushing it up. There's no arrow pointing up. And if by the time we're done with this, it looks like arrows are somehow unbalanced and it looks like there's somehow a net effect pointing down, that's why the thing is accelerating down, slowing. Okay, so long story short, or short story long, this is my diagram. This is my pure free body diagram of some moment, some point in space and time during the object's journey upwards. This is the pure free body diagram. There's nothing else in it. Gravity pointing straight down, friction pointing down and to the right, normal pushing up and to the right. That's the pure free body diagram. Now, there's more I have to do with it, of course. And we eventually have to look at the down picture. But if you really understand the up picture, it's pretty easy to adjust for the down picture. So what am I going to do? Like, what's the point of this? The point of this is that I'm going to ultimately collect all these forces and put them on the left side of F net equals ma, and thereby predict something about A. All right. Hold on. Okay. And I'm watching the, okay, we've got 25 minutes. Okay. So we're making this diagram. The purpose of this diagram is to force us to know exactly what forces are acting and in what direction, right? And it really is, it's that. It's like, this is all about F net equals MA, or sum of Fs equals MA. But the purpose of the diagram is to know exactly what to plug in for the Fs, which really is the tricky business of physics. Okay, so the diagram forces us to know what the Fs are and in what directions they're acting. And the way we know that is by doing this rule in our mind, like the one touch, one force rule, which has two exceptions: gravity, which is no touch at all, and surfaces pushing, which actually have two forces for every touch. Okay. Okay. So we make this whole diagram, and then the purpose is going to be to add up the arrows and like plug in the arrows to the left side of F net equals MA to add up all those arrows and say, aha, the sum of these arrows will give us the A of that M. But what I was saying before really starts to apply now. F net equals MA is a vector equation. What it really is a package of three simultaneous but independent equations, like one for each axis of space. F net equals MA is true, applies independently but simultaneously on each of the axes of space. Okay. Um, the problem with our diagram right now is we've got arrows going in all kinds of directions. We've got arrows, some arrows are on axes, if you like, but some arrows are not. Like, not all of our arrows are perpendicular or parallel to each other. So what we have to do, and this is what gets into the final exam and stuff like that, what we have to do is just like what we did with vectors in lab 3, when you dealt with displacement vectors, the whole island thing. What we have to do is choose a coordinate system and break up vectors so that each vector is viewed as the sum of its components lying along particular axes. Galileo says we're allowed to do that. In fact, Galileo says we have to do that. Galileo says the laws of physics are going to be true in any unaccelerated reference frame and in any coordinate system you pick. You're allowed to pick whatever coordinate system you want, and physics will work out. But you have to know what coordinate system you picked, and you have to stay in that coordinate system. And even though all coordinate systems will work out equally correctly, some coordinate systems are a lot more convenient than others. So we have to make a choice. I mean, this is all goes back to Galileo, always. So we're going to choose a coordinate system and then break up our force vectors into components that lie along those coordinate axes. This ultimately is called making a component diagram. So we're taking our pure free body diagram and we're now going to adjust it or break it up or manipulate it so that some of the vector forces that we have in there are actually broken up into smaller component vectors. I'll show you what I mean. Okay, just to summarize again what I just wrote there, like we're going to choose a coordinate system. What do I mean by choosing a coordinate system? I mean, we're going to make a decision like where's our x-axis, how is our x-axis oriented here, and thereby how is our y-axis oriented. Now, one thing about a coordinate system is all the axes by definition are always perpendicular to each other, to one another. So once we pick our principal axis, our x-axis, then our y-axis will necessarily lie at 90 degrees to that. And in a case like this, I don't care about, nothing's happening along a z-axis. Like this whole problem is two-dimensional for all practical purposes. So what I have to do here is pick an x-axis. Put another way, I have to take a piece of, in my mind, I'm going to take a piece of graph paper or like a transparent piece of graph paper and like hold it in front of the situation. And I'm going to line up the blue lines of the graph paper in a certain way. No matter what way I hold the graph paper, like the physics should still work out. That's in effect what Galileo is saying is like, it doesn't matter how I hold my graph paper, nature is still nature. But the way I hold my graph paper in my mind will make a big difference as to how easy it is to solve this problem. Like any way will be correct, but some ways will be a lot easier than others. So, and any way will be correct only if I'm consistent with that way. So I have to make a conscious choice here about what do I mean by my x-axis. And the strategy is that I'm telling you for all time in physics, the best strategy, and this again is what the final exam is trying to get into, strategy and this is for all time. This is a rule. If you want to memorize anything, like memorize what I'm about to say, it will be true for the rest of physics. As a strategy, choose okay, this is a subtle point, and of course I wrote it illegibly, but what I'm saying is we're going to choose our principal axis, what we would generally call our x-axis. Like sometimes the principal axis is not called x, and it doesn't matter what it's called. So, but your main axis, what we're going to call our x-axis, and specifically the positive direction of our main axis, we're going to line it up with the direction that we expect this thing to be accelerating along. Okay. Now I expect this thing to accelerate along the plane. Like I don't expect it to fly off the plane. I don't expect it to fly into the plane. And I also don't expect this thing to accelerate straight down. Like it's not in free fall. I expect this thing to slide along the plane. And as I was pointing out before, not only I expect it to slide along the plane, and I know that right now it's actually moving up the plane. It's velocitizing up the plane. But remember, velocity and acceleration, while related, are not the same thing. If I really think this through, I expect this thing to accelerate down along the plane, i.e., even if it's moving up, I think it's going to be slowing down while it moves up. I think it's going to be accelerating opposite to its direction of motion. And by the way, similarly, while the thing is moving down, I think it's going to speed up. I think you know that. So either way, I expect this thing to accelerate down along the plane. So I'm going to say, that this, if I'm drawing this right, I've almost forgotten which way. Yeah. I'm going to, and this is what you did in the lab, like whether you understood this or not, I'm in effect tilting my graph paper in my mind. I'm tilting my graph paper to line up with this slide. because I think that this slide is the way that the object's going to accelerate. And therefore, this will become my positive y-axis. I'm making that decision. I'm lining up the coordinate system with the situation on purpose. And why? Because f net equals ma, if I like I could do this other ways. And you might even think that this extra step is weird or hard or something. But the truth is, if I don't do this extra step, if I just like walk in and keep thinking that the x-axis is horizontal like it always was, if I in my mind am holding graph paper that's like that, then the thing is that the object is not going to accelerate along what I'm calling the x-axis. Therefore, I'm going to have to talk about it's going to accelerate like off in some weird way. So I'm going to have to divide that acceleration into two components, an a cosine component and an a sine component. Like I'm going to introduce sines and cosines right away, right on the right side, if I don't make this decision. And then I'm going to also have sines and cosines on the left side. It's going to be a mess. I mean, it's possible, and you'll see that on the final exam, but it's going to be very messy. So what I do to minimize the number of components or cosines and sines is I tilt the whole thing to line up with A. So that's what I do. And so now I say, with this decision in mind, I draw a component free body diagram. I'm going to take the vectors that were in my pure free body diagram, and I'm going to break them up into components that lie along these axes. Like in the end of the day, I only want arrows that are along axes, because then at the end of the day, I can add up all the arrows on one axis and say f equals ma on that axis, and I can add up all the arrows, including minus signs, on another axis and say f equals ma on that axis. F equals ma applies independently but simultaneously to each axis, but I need my arrows to lie along axes in order to do that computation. So I now make a component free body diagram based on this decision. Whoa. Okay, so now, and again, if you look, I think this is what's going on in your lab 5, and you'll see this is what's going on in the final exam. We've made our pure free body diagram, which is just like a snapshot of what forces are actually occurring, what the forces are like actually doing, no matter how you look at it. Now we're superimposing that free body diagram on a piece of transparent graph paper in our mind. And we're taking every arrow that was in our original pure free body diagram, any arrow that is not lying along an axis, we're breaking it up into two components that lie along axes. Okay, the whole principle here, I mean, without getting too bogged down, I mean, this all goes back to lab 3 in a way, which we discussed somewhat, not a ton. But the whole principle here is that when you walk northeast, you're actually walking somewhat north plus somewhat east, if you see what I'm saying, that any diagonal direction that you ever go in life is really the sum of some amount along one axis plus some amount along another axis. And you totally really know that if you live in Manhattan, or, you know, and if you go to school in Manhattan once upon a time, like, you know, if you have to get northeast, if you have to get uptown and crosstown, You go somewhat uptown and you go somewhat crosstown, and there you are, right? So we're doing the same concept here, only we're doing it with graph paper that's tilted in our mind. So it's a little bit funky. But in other words, what I'm saying is this. What we had, just to remind you, I'm just like recopying for the moment, we had an FBD that looked like this. Right, we had three forces in our free body diagram. Two of them are perpendicular to each other, but one of them is just like pointing down. Let me point out further. The one that's pointing down, gravity, up until this point in our lives, or up until this point in physics, you might look at that diagram and say, oh, gravity is nice and vertical. It's like nice and easy to deal with. And it's like the normal and friction that are like cockamamie. And you might be right if you were just looking at it, looking at this like in and of itself. But we know that this diagram looks this way because there's a track and an object like sliding along a track. And what I'm trying to say now is we just made a choice. We just decided in our minds to line up our graph paper, our mental graph paper, with that track because we think all the action is going to happen along that track. So if you tilt your head or you tilt the graph paper of your mind, which I wish I could quickly, well, I'll try. If you tilt your coordinate system the way we're suggesting, and this is a dangerous thing for me to do because you shouldn't really put what I'm doing, you really shouldn't put in your diagram. I'm just trying to say it for your sake. Like we're saying, here's the graph paper in our mind, like it's going like that. We've tilted the graph paper to line up with the situation. So when we think of it that way, it's really gravity that's off kilter. Gravity is the thing that's doing something funny. Yes, gravity is pulling straight down to the center of the earth, but nothing in our situation is actually moving or accelerating straight down to the center of the earth. In other words, gravity is really, by pulling straight down, in our situation, gravity is really doing two jobs. It's somewhat pulling the object in, like I'm saying this, gravity by pulling straight down is somewhat pulling the object against the surface. Like to some extent, the weight of the object is keeping it from flying off the track to some extent. And to another extent, oh, no problem. Thank you very much. I totally appreciate it. Private chat person. Got it. Thank you. Totally appreciate it. Thank you. See you soon. Gravity, the weight of the object is doing two jobs here. And both jobs that it's doing are sort of only partial. The weight of the object is partially holding it against the track, i.e. preventing it from flying up off the track, but partially the weight of the object is what's sending it along the track. In other words, here's the component free body diagram. The normal is doing what it's doing. It's along an axis. I'm not messing with it. The friction is pointing along an axis. I'm not messing with it. But gravity, I'm going to divide into two jobs, each of which lies along an axis. Like to some extent, gravity is doing this. And to some extent, gravity is doing that. Like it's gravity's pointing in the same. Sorry, let me just get the chat. Sorry. Okay. Okay. Like the gravity is really doing two jobs. It's to some extent pointing against, and to some extent it's pointing along. When I say extent, I mean a fraction, like somewhat, just like, so I'm going to label those two arrows in a moment, but remember from vectors in general, if I have a vector like this, right? If you're walking z number of blocks, if you're walking z miles to the northeast at some angle to the northeast, that really means that you're walking some extent to the east plus some extent to the north, right? Where did I get sine and cosine from? SOHCAHTOA, right? Like. I'm just saying this quickly because I think you know this, but the whole principle of vectors, and this is still all Galileo's principle. This is all just saying whatever the laws of physics apply to each coordinate system independently. So when you walk, and you could put in numbers here if it makes it easier, like say z equals 10 and say theta equals 30 degrees. If you walk 10 miles at 30 degrees to the northeast, that is equivalent to walking 5 miles to the north and 8.66 miles to the east. Like I mean, I did that in my head. You can check that, right? But right. How else can I put this? Because sine of theta equals opposite over hypotenuse, that means the opposite side of the triangle equals hypotenuse times sine. That's what I'm quickly trying to say here. Again, technically, this is like a reminder or whatever. But what I'm saying is this concept, if you understand it with displacements, and you did in lab 3, then it's true of any vector quantity at all, whether displacements, velocities, accelerations, forces. So I'm saying here, and I know we've got 4 minutes left, but we're actually almost there beautifully. I'm saying that what we could have looked at as gravity, as one big hypotenuse, is actually the sum of two components, mg cosine and mg sine. It looks a little confusing because here gravity looks vertical, right? So what I'm doing is I'm saying that there's a right triangle built in there, and I'm sort of conscious of the time, so I don't want to like draw too much right now, and I can go back over this on Monday, or you can think about it. But I'm saying that you could really look at. Okay, be careful. You shouldn't really put what I just did. You shouldn't really put it in the pure free body diagram because it's confusing. But I'm just trying to show you now as a class that right triangles are right triangles, even when they're tilted. And hypotenuses can be straight up and down, even though we're used to thinking of hypotenuses as diagonal lines, and we're used to thinking of right triangles as having like a vertical leg and a horizontal leg. But what we're trying to say in physics is even when you tilt your head, physics should still work. And in fact, sometimes it's good to tilt your head to make the physics work more easily. So I'm saying that that force that's pulling straight down really is actually pulling at an angle compared to everything that's going on. And it really, that gravity line can be viewed as a hypotenuse that has two legs, one, and each leg must be smaller than the hypotenuse. So and sines and cosines, remember, and I know I'm watching the time, I know there's 3 minutes left, but remember, sine, no matter what angle you ever type into, whatever number you ever type into your calculator, if you then hit sine, you're always going to get a number like less than 1 or greater than -1, right? Like it's always going to be the answer to the sine of some angle is always a fraction or a decimal, but I'm going to call it a fraction. And same thing with cosine. So if you take a hypotenuse and you multiply it by cosine or sine, what you're doing is you're looking at just a fraction, a smaller amount than the hypotenuse. That's why legs of right triangles are always smaller than the hypotenuse. So I'm saying the weight of this object is pulling straight down, but ultimately that means a fraction of the weight, a fraction called cosine, is pulling it against the plane, and a fraction of the weight is pulling it along the plane. And if you're vaguely following me, one question you might have is, how did I know which one to make sine and which one to make cosine? Very fair question. And there's a number of ways to see. Since I only have 1 minute left, like you can do out the geometry and you can see, but the fastest to know, oh, and someone's come, oh, okay. But one thing I can tell you is this will always be true for inclined planes, but the fastest way to know that I'm right is the sine of 0 equals 0. Right? And sines get bigger and bigger as the angle gets bigger and bigger. The cosine of 0 is 1, and cosines get smaller and smaller as you make an angle bigger and bigger. So if you just look at the limiting case here, we're saying if the angle were 0, if this plane were horizontal, then gravity would not be shoving the thing along the plane at all. It would be fully holding it on the plane. And I'm saying that fast, but just think that through. So ultimately, there's 30 seconds left. What I'm saying is the component free body diagram, and I may be going 60 seconds over here. I apologize, but this is the heart of the whole thing. The component free body diagram then looks like this. And the purpose of all of that is now, and I apologize if you have to go. I'm going to take like 60 more seconds just to finish this up right now. This is now a diagram. I mean, those arrows are, there's 2 arrows going down and there's 2 arrows going along the other axis balancing each other. Now we can do F net equals MA along each axis separately. And we can say y-axis, and I apologize if I'm taking too long, you can go and you'll get the notes after. But if we look at the y-axis, we're literally saying n minus mg cosine theta equals MA. And along that y-axis, because we deliberately set these up this way, along the y-axis, there's no acceleration. The block's not flying off the plane or crashing into the plane. It's 0. So the normal force is balancing mg cos theta, a portion of the weight. And on the other axis, and then I'm done, on the other axis, we have mg sine theta plus friction equals MA. And there is acceleration along that axis. And notice the mg sine theta and the friction are working together, yanking the thing down the plane. All of this is exactly what you would do. So here. So when this thing is on its way up, the weight of the object and the friction are both working together to produce a huge net force and a huge acceleration, granted pointing down. If you're thinking ahead to when the object's coming down, everything I just did would be exactly the same, except when it's on its way down, friction points up. So on its way down, so I'll just write this. Sorry, I'm taking so long, you can go, but just so you can have this down would be mg sine theta minus friction equals MA. Same friction, same mg, same everything, but friction would flip. On the way down, friction would point the other way. So oddly, when the thing's on the way up, there's a huge net force against it, a huge acceleration. It loses speed really, really rapidly and gets to the top really rapidly. On the way back down, gravity's pulling it down, but friction's pointing the other way. They're working against each other. The net force is smaller. The acceleration will be smaller. So on the way up, the thing loses speed at a rapid rate. On the way back down, it gains back the speed at a slow rate. It never gains back all the speed that it originally loses. So it zooms up the plane and then trickles down the plane. That's the summary of this whole thing. We'll talk more on Monday. I know where we are. I know what you need to know, blah, blah, blah. You are great. Thank you for being so patient. Nothing more is due. Just keep looking at the final exam and see what questions you have for Monday. Okay, thank you. Thank you. Thank you very much. Have a great day. Have a great weekend. Yes. Mark less of it. Oh, yeah, no, you should go. Wait, no, yes, you're not interrupting. Yeah, good. Go. Yes, bye. Thank you very much. Sorry for, yes, good. Thank you. You enjoy your weekend. All right.